Welcome to Kitchen Table Electronics. This is an online laboratory class where you will learn basic electronics, but in addition, the skills needed to use microcontrollers and computers to control electronics. This class is being developed primarily as a 300-level online laboratory class, an online class that you can take by working at your kitchen table, as the title suggests. It is for physics majors in a new online physics degree to be offered by Arizona State University. But before you get scared off, I'm going to present the class at a general level so that most of it will be accessible to students in any scientific discipline who want to get familiar with modern laboratory instrumentation and computer control of electronic instruments. We will cover what everyone covers in classes on electronics: resistors and resistor networks, reactive components like capacitors and inductors, nonlinear devices like diodes, active devices like transistors and op-amps, and the tools of the trade like the digital multimeter, signal generators, and oscilloscopes. But what's new about this class is we're going to do it using our own computer coding and our own microcontroller. Electronics without computers would be like learning Latin, not very useful in this day and age. Instruments from the largest, like this MRI machine on the left, to the smallest, like this digital thermometer, are controlled by computers and microcontrollers. And so there's really no point learning electronics if you don't learn how to interface that electronics with a computer. Another aspect of this class is data analysis. Computers have allowed us to take millions, billions times more data than we could in the old days when we sat in a laboratory with a notebook and a pencil. And to analyze this data, we need computer programs. These screenshots are a couple of contemporary data analysis programs. They cost an awful lot of money, and I have found them as hard to master as developing my own ability to write computer code. So I've decided to abandon these commercial products and teach myself a programming language so that I can analyze data as I want, and my time spent learning how to do it is then more universally applicable than my time wading through these commercial software products trying to understand where to find the right buttons. Now, I said this was kitchen table electronics. We're going to do it using our own computer, which presumably you have if you're watching an online class, to control our experiments, to collect and analyze data ourselves. And we're going to do it all for about the additional cost over and above the computer of some leading texts in the field. I'll give you an example here, and if you buy the text and lab manual, you'll spend a little more than I am proposing you spend on building your own kitchen table lab. And when you've finished, you can keep your own pretty nice digital oscilloscope, and in addition, you will have a signal generator, or you can sell them on to another student. So you get to keep your own lab at the end of the course, which is actually a pretty good bonus. How on earth can it be possible to do this for so little cost? The reason is a set of open source tools. This is software that has been developed by a community of users and is kept up to date and improved by a very large community of users, primarily the computer language Python, which is very powerful, relatively easy, and we'll say more about in a minute. For microcontrollers, we're going to use the Arduino, supported by also a very large community. And finally, we're going to use some open source software called Fritzing for laying out our electronic circuit. You'll also have to buy a few tools, fairly inexpensive, with the exception of the digital oscilloscope, which will cost about $100. The rest of the items here all cost between $30 and $10. There's the toolkit, including digital multimeter and soldering iron, some breadboards and connectors, the Arduino microprocessor, and a chip for synthesizing AC voltages over a large range of frequencies. The shopping list for this hardware and links are all contained on the homepage for this course, and I'll give you a pointer to that at the end of this introductory lecture. You'll need your own computer, of course, and hopefully you'll have at least one USB port and a USB expander, or if you've got multiple USB ports, you'll be just fine. Now, we're going to use Windows 10 in our examples. However, if you use a different platform or operating system, you can find detailed instructions on how to install and operate the various open source pieces of software in a book, an online book, which I strongly recommend, by Patrick Desai, which is Python programming for Arduino. So let's talk about Python. It is now the most widely used computer language in the world. This is a relative estimate of users from the Stack Overflow blog, and the orange line is Python versus time. And you can see not only is it the most widely used language, but it's also gone from 0 to that position in a very short time. And that's because of the advantages of Python. It's an interpreted language. What that means is you can sit at your keyboard in the Python interpreter, type in a command at the prompt, which looks like these 3 chevrons here, hit return, and your computer will execute it. Now, I have to say I was terrified of Python because I remember BASIC. Python is not BASIC. It's a very powerful language, and you can put sets of instructions together in an editor and then run them through the Python interpreter, and it turns out to work very well and very nicely. The main feature of Python is that it is a modern object-oriented language. This allows for the construction of something called classes. These are collections of functions and data organized in a particular way that when you tell the interpreter to import a class, and then from that class cause an instance of a particular method to create an object, which all sounds like a lot of new words, but all that means is that in the class you've got a set of codes, and you extract, for example, one, you call it something, it becomes a block of executable code that the interpreter knows how to get to, and it can be called by the interpreter over and over again. The instructions that do this would look something like object, and it can be whatever name you want to call it in your code, and then the name of the class, and then with a dot, and then whatever the name of the method is, and it may have some argument that you would put in parentheses. So it's very simple to call the millions and millions of lines of code in the thousands of classes that people have assembled for anyone to use who is using Python. The layout of Python code is a little different from some of the other languages you might have encountered. It uses the white spaces on the page as a control. So this means that if you make a call to some routine, for example, if you define a subroutine with a DEF, name of the subroutine, open close brackets, colon, then the next line that is going to be the definition of that subroutine and the subsequent lines in that subroutine would be offset by a paragraph indent, and then you would remove the indent when you go away from defining your subroutine. The same applies to conditional statements like while and iterative statements like for an index lying in a range, please repeat the following set of statements. They will all be indented, and the end of the indent signals the end of the collection of code to execute conditionally. You'll get examples of this and see it. It's not hard, but you will surely occasionally put accidental spaces in your code, and the interpreter will come back to you with a nasty warning message. It's case sensitive, so you can't throw in capital letters for keywords. You can put capital letters anywhere you want in variables you define, but be sure to use the same mixture of lower and uppercase letters when you call that variable. But when you use keywords or functions you've defined, then it's very important to use the appropriate capitalization or lack of it. Something that is really quite unique about Python is it is dynamically typed. With other languages, you have to tell the interpreter, this is going to be an integer, so please reserve 2 bytes of memory for it. Or this is going to be a logical variable, so please reserve 1, and so on. Python figures out what to allocate in the memory based on the context of the statement. So for example, if you say x equals 1, it will figure you want to use an integer for x. If you say x is 1.0, it will figure that you want a double, i.e. a total of 4 bytes of memory set aside. There can be some complications, and we'll talk about that in the section on Python. You can download Python from the website python.org. It includes a so-called Integrated Development Environment, IDE. The included IDE is called IDLE. I happen to like it a lot. You'll see some criticism of it and suggestions that you download some more elaborate IDEs. I like IDLE because not only is it simple and straightforward to use, but by default, all of the Python files go places that IDLE knows to look. If you use other environments, you are going to have to spend a lot of time finding out where to tell it to look for various files. The basic Python download includes an incredible number of tools, but there will be other tools, tools for graphing, mathematical analysis, and so on. And there is a program called pip included with the Python download that you run from the Windows command box, not the Python interpreter. You go to the Windows command box and say pip install whatever the extra tool set you want is. Examples of these packages include the numerical analysis package, NumPy, which has an amazing number of routines in it, but you'll often call it for fairly simple numerical things. An incredible range of plotting and curve fitting routines in matplotlib. This is the library that has essentially displaced the commercial graphing and curve fitting software that I used to use. Very, very powerful and very, very nice. There is a graphical user interface which actually is included in the basic Python package, KTE Intro. There's serial input and output for talking to things like outboard microcontrollers, PySerial. And there's machine level control of outboard microcontrollers in something called PyFormata. And that's a set of tools we're going to use the most because that minimizes the amount of microcontroller coding that you're going to have to do. And there are lots more. You can, if you want, download, for example, an artificial intelligence package. And I'm told by the folks who use it, it's pretty incredible. And maybe you want to go get that before your next exam. Okay, so once the packages have been installed, you access particular classes from them by a statement in your interpreter that looks like import, for example, matplotlib.pyplot as PLT. And that then sets up an object in your code called PLT that is in fact matplotlib.pyplot. So this is an illustration of the object-oriented nature of the programming. Everything in Python can be an object. So if you say x equals matplotlib.pyplot, then if you print x, the interpreter will tell you that it is an object sitting at a certain point in memory because it's the collection of data and functions that is contained in the pyplot attribute of matplotlib. So very powerful, but you'll see when you use it, it's quite simple to use. Finally, it runs a lot faster than you might expect from an interpreted language. Once again, my experience was BASIC, which was pretty excruciating. The point being that what the Python code does is act like a shell or a collection of sort of top-level instructions that point to these lumps of code you have extracted as methods from the various packages. Those lumps of code are themselves compiled in machine code, so most of the hard stuff is done very quickly on your computer. And then finally, if you really don't want to see the Python interpreter, if you want your code to look like an executable file that you can run in Windows as you would run any other executable file, guess what? There is a program that will turn your Python code into an executable file and build you a Windows installer. It's called Py2X. So a few more things. Here's the link to the Python organization. Here's a link, this pythoncourse.edu. I have found fantastically useful. The Python documentation online on the python.org website is a little terse to read, to put it mildly. I found the Python course to be extremely clear, no excess verbiage to wade through, just very nice pointers as to how to understand particular aspects of the Python language. So I've used it a lot, and you probably will too. Here are some of the additional packages that we will download. The PyFormata is on the python.org webpage, and that is the software that will talk to our Arduino. The scipy.org has all the scientific computing packages. In particular, I mentioned NumPy and Matplotlib, but this is where you will get exotic things like artificial intelligence if you want them. And if you want to write mathematical programs, this is where you'll go to get the tools. Now we go to the next star of our show, which is the Arduino. It's an amazing little thing. You can buy an excellent knockoff board, which isn't really a knockoff board because all of the design for this is open source, but you can buy a board for about $10. If you want the genuine Arduino, you're going to have to wait a long time for delivery and pay about 3 times more. But here it is. This little board has a microcontroller, a USB port that you can communicate with your computer with, a power plug here, and then actually a serial lines here that will let it communicate with other chips and so on. It's programmed in another computing language, a version of C++, and when you download the Arduino IDE, you'll have a little compiler that you can use to build code for your Arduino, but it comes with so many example programs that we really won't need to code the Arduino. As I said, it'll run interactively via this USB port, and that's mainly how we'll use it. But you could also put a program in here and have the microcontroller execute it in a standalone loop, and we will illustrate that in the first lesson. The Arduino uses, the Uno, the one we'll use, has a microcontroller called an ATmega328. It doesn't run very fast, 16 megahertz, has 14 digital pins, 6 of which can generate analog signals using a technique called pulse width modulation, and we'll introduce that early on in the class. And it's got 6 analog input pins that will take some varying voltage and convert it to a series of numbers. There's 32 kilobytes of onboard flash memory, which is actually enough to do some pretty complicated things. It acts as its own voltage source. It has a 5 volt and 3.3 volt output pin. So we're going to use the Arduino as our power supply for the course. No need to buy an expensive power supply. You can get a limited amount of current from the 3.3 volt pin, a lot from the 5 volt pin, but there are some limitations to do with how much voltage you drop from an external power supply if you use one. Fritzing is the third wonderful given away thing that we will use in this course. It's for circuit layout and design. So this shows you here a Fritzing layout where one can click and connect points on the circuit and then hold down the mouse and make these bends and so on, so you can follow where to put wires in a breadboard to connect to your external circuit. It has a second view, which when you click on, then generates this nice schematic diagram, and then a third view, which makes you a printed circuit board. Generates a file that you can send off and have a professional printed circuit board made. So it's really a nice, handy piece of software to have. We're going to use it as a reference because you can do things like put component values in and get a picture of a component. So we'll use it for lots of things, and I recommend you download this too. Okay, we turn finally to an overview of the course. We'll start off by installing the Arduino and the IDE that comes with it. We'll then use our Arduino in Module 2, where we will introduce the fundamentals of electrical measurement, use the Arduino as a source of voltage, and at that point introduce the wonderful operational amplifier. And then we will use our oscilloscope to take a look at a voltage that changes with time and the pulse width modulation output of the Arduino, which is what is used to generate DC signals. And we'll show you how to generate a DC voltage using pulse width modulation under computer control. In Module 3, we will go to Python programming. We'll install the Python package, cover some Python basics, and then we will introduce some Python programs. Throughout this course, I am going to be giving you the Python code for the lab experiments you're going to carry out, but you will write some of these programs in this module. And then I've thrown in an advanced topic just for fun on graphical user interface programming, because that is fairly straightforward to do in Python, not needed for this class, but fun. Module 4 will introduce the pi-fermata methods of Python, which are used to directly control the Arduino. And the first thing we're going to do is build a plotter that plots the current voltage characteristics of devices. So it outputs a voltage from your Arduino, measures the response of some circuit, records it on the Arduino. Then we're going to use our plotter to look at nonlinear devices. The first of these will be the diode, and you'll have great fun here because here you'll record a fairly complicated response from a little device, and you'll fit it with a theoretical model, so you'll use all of the tools you learned earlier. We'll then carry on with other nonlinear devices, the Zener diode, importantly the transistor, and the field effect transistor, all of which you'll measure with your curve plotter. Once you've measured the transistor and understood its response, you'll then be in a position to design and make transistor circuits like an amplifier, and that will end that module. There is an advanced topic on the math of the RC time constant. Finally, we will introduce AC circuits and reactance and impedance. To do this, we'll need a signal generator, so we will introduce the AD9850 digital frequency synthesizer. In the next module, we'll make a peak detector that will record on your Arduino the peak value of a sine wave circuit using an operational amplifier, actually two of them. Then we'll use this to explore capacitors, and then circuits that include capacitors and resistors, and then inductors, and circuits that include capacitors and inductors. Finally, we will make a digression to discuss the topic of Fourier analysis. And then in this section, there are 3 advanced topic modules on math, one on RMS voltage, one on complex analysis, and then another on analysis of the RC circuit. And then we'll end this course with a little module I've called Tips for Lab Rats. And these are just some practical hints and tips that are not included in basic electronics classes, but are sort of important to know when you go to measure things in a real lab environment. Finally, if you're taking this class online, you'll be doing it through an ASU portal, but I'm putting this material up for public consumption on this Wix-hosted website here. So if you know anybody who wants to learn the basics of electronics but doesn't particularly want to register for a physics class, they can go here and cover the same material that you're getting in this course, except of course they won't get a grade out of it. So that's it. Thank you very much for listening to this introduction, and enjoy the rest of the class.